Hi, and welcome to another one of my short little videos about physics and astrophysics, astronomy, however you want to go out and name it. Today I think is especially exciting for me, this video, because at last I'm going to talk about what I am spending most of my time doing right now. That is gravitational lensing. And now I've made some points up here on the board that I would like to go through, get through during this or perhaps another video, maybe more. I don't know yet. It depends. I would like to state two things right away. The first thing is that these videos, no matter how many I might be doing about this subject, shall not be considered in any way any kind of introductory course or something like that in gravitational lensing. It's simply me talking about what I know for now and what I've been doing so far. Now I'll be leaning myself strongly on this these papers. It's lecture notes from I'm not sure how to pronounce it, Saas-Fee course in gravitational lensing, and I will particularly be using the first part, which is just a basic introduction, and then the second part I think it is, which is about strong lensing. So that's the first thing I would like to say. Don't consider this a course, introductory course or anything like that into gravitational lensing. More see it as a general introduction, like to the wide public about what gravitational lensing is. Now I will try to exclude as much math as I can, but there will be math. It will mostly be simple derivations and geometrical constructions. Alright, let's get started. So I think that what any kind of introduction to gravitational lensing, just basic introduction to the subject, would have to have is the following. First, I'd like to go into the basic idea of gravitational lensing and some part of the history. This will actually be reversed probably. Then there is the most fundamental equation in gravitational lensing. It's the lens equation. I'll be spending some good deal of time there. Then we'll go into magnification. I'll talk a little about what that is. Critical lines and caustics. I also feel that those are important, because from this you can actually derive how many images, as we call it, you would expect to see. And lastly, I'll loosely in between I'll give some examples. All right. So I will pause the video now, and then I will draw something new on the board, and then continue. All right. Welcome back. So the funny thing about this kind of introduction to gravitational lensing is that I will actually be starting this introduction by talking about the sun. Now, Newton actually postulated, or what do you call it, thought about that the massive pull, the gravitational pull from the sun, might be able to deflect the light from distant stars. Now at that time telescopes weren't that evolved, and we didn't have they didn't even have photographic plates, so all you could see was what you could measure with your naked eye. And looking upon the sun, even under an eclipse in a telescope, without any means to block out the light or anything like that, can be considered a tremendously stupid idea. But he postulated it, and later Soldner some years later, Soldner actually also calculated the deflection, and what was calculated was this. The deflection angle should be 2 times the gravitational constant times the mass, in this case the sun, divided by the speed of the light squared times the radius. And when you're talking about the limb of the sun, you usually just use the radius of the sun. All right. Later, however, in 1916 or 12, something like somewhere around that, Einstein actually first came with general relativity, and from that he actually first calculated this value, but he later redecided and recalculated from general relativity, and got that the deflection angle instead should be 4 times g, the gravitational constant, times the mass, again here the sun, divided by c, the speed of light, squared, times the radius of the sun. Alright? And again the limb of the sun. Now I won't be writing up the numbers because you can just go on the internet and find these numbers, but I've used that the mass of the sun is 2 times 10 to the 30th kilogram. The gravitational constant is 6.62 times 10 to the minus 11, and the constants in meters squared, meter cubed, blah blah blah, so on. I said that the radius of the sun is 6.96 times 10 to the 8th meter, that's 8, and the speed of light is 3 times 10 to the 8th meter per second. Alright, so when you use these two formulas and you put in the relevant numbers, like I just read out, then when you calculate the deflection, the Newtonian deflection angle, you get, first of all, if you do this by yourself, and I certainly would suggest you do it, please, when I postulate anything about a calculation, try to redo the calculation and see if you get the same numbers. Then remember that what you get by calculating this deflection angle is in radians. So in order to get this number in arc seconds, you have to multiply this number in radians by 206,271. Let's just put, I would put that number up here. Just put it down here. Let's say radians to asec is 206. Sorry, that's a 6. 271. I hope you can read that. But otherwise, I'll also put links up on this video to the article by Dyson, and what else you need to know in order to get this subject. I think I can probably also provide links to I have all the lecture notes from the Saas-Fee course. I can also put that up if needed, but otherwise you can easily find them on using archive or something like that. Alright, so now we have two predictions. Sorry, I forgot to mention that when you use the Einsteinian, or how you want to call it, deflection angle, you get, sorry, I didn't get that far. Sorry, let's just start again. The deflection angle from the Newtonian deflection angle is 0.87 arc seconds. When you make the same calculation using the Einsteinian deflection angle, you get radians, then you get 1.74 arc seconds. So now I would claim that the board is set. Alright? We have two different predictions that are very different from each other. One is by Newton, or Newtonian, and the other is by Einstein or general relativity. And there's a huge difference. So before that, there was other predictions that came out from general relativity, that was confirmed. But this was sort of the last piece of the puzzle. This was actually the masterpiece. If this also turned out to be correct, or in agreement with the prediction made by Einstein, then the coffin would almost be sealed on Newtonian gravity in a broader aspect, because as we know, Newtonian gravity still works here on Earth. We still use the formulas. We should actually solve all this using Einstein's field equations, but that would make every calculation we do horrible complicated, whereas when you solve it all out, it still falls back to the Newtonian examples. That is how general relativity is invariant with Newtonian gravity here on Earth. All right, but now we have these two predictions. What would be better than try to see this, try to measure this? So in 1919, or actually a bit before, because they had to get into, it took some time to travel. Dyson, Eddington, and Davidson traveled to two islands, and of course I can only remember one of them. It was called Sobral, or Sobral. I can't remember the other name, but that's really not important. They measured this. They found out that we had predicted that in that year, 1919, there should be 1919. There should be a solar eclipse that would be visible somewhere across Southern America, Brazil, and over to the coast, an island out of the African coast. So that's the two islands. They measured this, and what they found by using, at that time, incredible machinery, but I'm really stupefied at what kind of measurement they could actually do. So let me try to just shortly run through what they did. So they took apart some telescopes and brought with them on a ship, and then they used some sort of clock mechanism. We also have that same kind, just in a very modern version here in Denmark, on something called Warfield Observatory. It's an old observatory that was first used by the university, but when we then shifted all the telescopes to about somewhere around the equator, because that's where the conditions are best and up in high altitudes, then this has more become a museum, even though the telescope is still functional. That's really not important, but the same kind of clock mechanism, simply a clock that makes the telescopes follow the movement around on the sky. They used that. They also used some kind of special photographic plates that they put into the telescope, took pictures of the sun during the eclipse, and they also took pictures of that same area with these stars before the eclipse. So you would have two images, one without any influence, just pictures of stars, and then you would have another image of a solar eclipse with stars that might be deflected. That was what they wanted to find out. And so they came home with those photographic plates, and then they used some sort of device. I've never seen it before, but I find it extremely interesting that they used some sort of device where they had a little pin. They put up the photographic plates, and then they had this little pin they could move around by clicks. So one click would compare to a certain degree of movement. Now they also had some way of recalculating these clicks they used to arc seconds. So that is really, I'm today, what I would do today, I would take an image of the stars, and then also take an image of using a CCD, of course, and then take an image of this solar eclipse with the stars. Then I would plate solve the whole thing, put it into a program, and then just measure the distance between the stars and the limb of the sun, or whatever you want to do, the difference between them. There's no clicking. I would just get the numbers straight out in degrees arc minutes, arc seconds, whatever I want. But they use these little click mechanisms, and really, I find it incredible that they actually could do it. But by taking these two measurements from Sobral and the island, or maybe Sobral is the island, I can't remember, and then taking the mean and putting some errors on it, they found that the deflection from the limb of the sun through the stars is consistent with 1.61 plus minus 0.30 arc seconds. This is, in my opinion, a perfect example of how science works. First of all, the 1.7, I actually think that they calculated 1.75, but that could be a rounding error on my part. I find it incredible that using this kind of tools, alright, they can get a number that is actually pretty precise. It's somewhat off, but it's within the uncertainty. So this measurement by Dyson, Eddington and Davidson was considered to being the last piece of the puzzle, proving that Einstein was actually correct. And this also kick-started the whole idea of using gravitational lensing, the whole idea of gravitational lensing, which I will continue by just making some other historical notes. I will do that after a pause. Alright, so now I'm back. I just had to refill my coffee cup. Cheers. Alright, so as I said before, I have raised the whiteboard, but as I said before, the measurements done by Dyson, Eddington and Davidson in 1919, or actually I think the paper was published in 1920, but in any way, really kick-started the whole idea about gravitational lensing. In this case it was deflection around stars, but in 1937 Fritz Zwicky published two papers, incredible papers, where he suggested that what he called extragalactic nebula, but today we just call it galaxies, could deflect the light from distant galaxies. Now this was something special. This was a prediction that had never been thought of before, and the prediction was somewhat well, to be honest, ill-conceived, because nobody really believed that, right? But that is why it was really a huge discovery when Dennis Walsh and others in 1979 discovered the first radio gravitational lens. Sorry about that. Discovered the first gravitational lens in a radio wave. That was an incredible, really incredible discovery. And they did that. They concluded that these images they saw, different images, was of the same source by doing, by calculating the redshift and also looking at the colors and seeing that both the colors, relative colors of these two images and the redshift was the same, which differed completely from what we would say today is the lens galaxy, the galaxy performing the lens. And then a year later, the triple quasar PG, or maybe I should write that up. Triple quasar PG, what was it? 1115 plus 180. that triple quasar was discovered, and then a lot of consecutive observations, especially including Einstein rings. Einstein actually predicted that when a source, I will get into what a source and an image is later when I introduce the lens equation, but Einstein actually predicted that if you had a source like this is the source, and you have the lens and me as the observer, if they are perfectly aligned, then what I would see, instead of having images all around, I would see a perfect ring around the lens, the lensing galaxy. And that was also considered to be highly improbable that this setup, perfect alignment, would be possible. And that is also why it was a major discovery when we actually found an example of a ring around a galaxy. Okay, and then later came giant arcs and all that we know from especially clusters. I have an example here. You can see it. This is an example of an arc. Is right here. This is the arc, and then one famous example is this of Abel 2218, I think it is. Yeah, 2218, where you can see a plethora of multiple images around, lots of arcs and all that around. Yeah. Now these are all this is from the images from the lecture notes, so you can go in and look at it yourself, and you can also sorry you can also take a look at the original article by Dyson and others from 1919. It's a long article, I would like to say, and for some people it might be sorry to say, but a bit boring to read, because they use a lot of space describing how they pack things up and the travel and how long it takes. It's sort of the first part of the article actually seems more like a diary, a travel diary, than it resembles an actual scientific paper that we would read today. But of course there's also huge time difference. But in any case, take a look at it, and then in the next video I will look into the lensing equation that is truly and absolutely the most fundamental equation you'll ever see in gravitational lensing. Now, if you want to do modeling and calculate certain aspects of lensing, then you have to know more. But in general, all you need to know about gravitational lensing is that you have to understand the lens equation, what that means and how it is derived. Alright? Welcome back to the second part of this video, where I will introduce and talk about the lens equation, and try to give an idea about what gravitational lensing really is. And I have shown some images and told you about the deflection angle, both from Newton and Newtonian gravity and general relativity and Einstein gravity, and also mentioned the measurement done by Dyson and others to actually confirm the prediction made by Einstein regarding the deflection angle around the limb of the sun. Alright, so in this video we'll take a closer look at the lens equation. But let's first I'd like to first start by sort of sketching out what gravitational lensing is. When we're talking about gravitational lensing that I'm working on, which is in clusters, but the basic idea is the same whether you're talking about micro lensing or galactic lensing, strong lensing, weak lensing, and so on. Alright? So on the board, on the whiteboard here, I have drawn, maybe I should put in some names. So we have the source here. I'll name that with an S. Then we have the lens here. I'll name that by an L. And then we have the observer out here. It's usually named with an O, but we also usually don't use the observer for anything other than to give a direction of the line of sight. Alright, so there are multiple dashed lines here, so I'll just take the straight one and talk about that. So this straight dashed line here represents what we would see of this source if there was no galaxy in front of this, or in this case a cluster of galaxies. If this weren't there, then what we would see would be the light from this galaxy in this straight line, assuming of course that we actually can see the galaxy. If it's too far away, if it's too dim and we can't observe it, then of course we can't see it, but here we assume that we can see it. Alright? Second of all, we have the lens here, and when we introduce the lens, we of course can't see this source because it's in the way. But because light is deflected around this galaxy or cluster of galaxies because of the huge mass in here, then what we would actually see is the image of the source. Maybe I should put an eye up here. The source, we would see it up here instead of here. And that is because instead of going in this straight line here, which we can't see, or anything in between from here to here, and instead what we see is actually the light coming in this direction, but since it is being deflected around the cluster, what we actually see is the source, the image of the source up here. And that is the same, basically the same thing what Dyson and others, Dyson measured around the limb of the sun, that where you would expect the star to be here, during the eclipse you actually saw it up here instead. And then you would measure the difference between here, the distance, this distance, in order to determine what the deflection around the limb of the sun was. Alright? So this is a basic sketch. Now, if we had to calculate gravitational lensing truly as we should do it, we would have to use general relativity, which means that we had to solve the Einstein field equations. Now, that would be a horrible piece of work, because the Einstein field equations is a set of 10 coupled tensor differential equations, and you have to put a lot of Christoffel symbols and what have you in it in order to solve it. It's a lot of work. It takes a lot of time, and to make a model that does this with the amount of images we use today, I think it would complicate things beyond recognition. Luckily for us, we can simplify things. And the first simplification that I haven't put up here, but I'll just state, is that we are what we would consider in the weak gravitational regime. Now we have two gravitational regimes. We have the strong gravitational regime and the weak. In the strong, we're usually talking about neutron stars, black holes. We can expect deflections in big or wide angles. We can actually expect deflections going all the way around something, around a black hole or a neutron star. That's the idea that if you stand on the surface of a neutron star, you can actually see the backside of your head, because the light from the backside of your head is deflected all around all around the neutron star, and you can see it. So that's big deflections and strong gravitational regime. In the weak gravitational regime, we expect deflections of small angles, and compared to a neutron star or black hole, this angle alpha here is small. And in the weak gravitational regime with small angles, we also assume, because you probably know, most of you, that when we're dealing with these kind of when we're dealing with angles, we actually have to solve the sine or the cosine or the tangent. But in this case, we can say that when you have the small angle approximation is that when the angle, when the angle is small, that is alpha is, let's say, I think it's much less than 1. I think it's that number. Then we can say that the sine of the angle is approximately just equal to the angle itself, or in this case we can say that the tangent of the angle is approximately equal to the tangent to the angle itself, to this number. So that's also an approximation we use, and we also know that we assume that we're in the weak gravitational regime. Another example, another assumption that we make is what's called the thin lens approximation, or thin screen approximation. You can use whatever name you want. What this basically says is that I should also introduce these distances down here. I haven't done that yet. So when we are using, you can find different papers, and they probably all use different names for these distances. But what I have grown accustomed to is that the distance from the observer to the lens is called dl. The distance from the lens to the source is called dls. And the distance from the observer to the lens, the source, is called ds. Now some people want to make this more consistent with the number of numbers below, or indices below, so they call this DOL, DOS and DLS. I don't want to do that. I think this is more simple. And then I also have another measure in here, and that's the diameter, the length of this cluster. That is, how much does the cluster fill in space, how big is it? And so the thin lens approximation, or the thin screen approximation, is that since DLS, this distance here, let's put that up somewhere, since we have that DLS is much bigger than diameter, and which is also much bigger or much smaller than the distance to the lens, we can say that this distance compared to this distance and this distance is insignificant. Typically you would say that the distance for DLS and DL are in the size of gigaparsec, and the diameter of the cluster is typically somewhere around some number of megaparsecs. So these numbers are very much larger, as I stated here, than this diameter. And then we say, as I said, that this diameter is insignificant, and that means if we had to do this really truly the hard way, we would have to integrate this deflection, because the deflection is sort of gradually being pulled. But since we can use this approximation, I'll take a short break. I need that, and then I'll go into this deflection later. Alright, so after a quick stop at the bathroom and a refill of my coffee, I'm ready to proceed. go on. Alright? So I talked about, before I had to take a small break, about why this diameter, this size of the cluster can be considered, assumed to be insignificant compared to these distances here. And that means that instead of having a gradual deflection that we most likely would have to integrate over, we had to sum up all the small deflection angles to get the correct deflection. We can assume instead, because this is a very, very small distance, insignificant, that the deflection instead is like an angle, like a straight angle, right? Maybe I should. This will be much more visible when I make up the board, when I draw the fundament for how to derive the lens equation. But for now, you just have to understand that since DLS is much larger than the diameter, and since that DL is also much larger than the diameter itself can be considered insignificant compared to these great distances, and that is why instead of having a three-dimensional mass distribution in space, we collapse it to do 2 dimensions, and that is why it becomes a thin lens, a thin screen. So we get, instead of getting a three-dimensional mass, we get a mass density, we get what you call surface mass density. I'll not be going so much into the surface mass density. I might just quickly browse it over to just introduce it, because it is in some ways fundamental also for gravitational lensing when you want to calculate things. But in order to just understand what lensing is, you don't really have to know what the surface mass density is. But I will shortly introduce it, because it also goes into some of the calculations, some of the model results I will be showing you. Alright, so I will just redo the board and then be back. Alright, so now I'm ready to continue my introduction for the lens equation. That is what I'm going to work on now. Now I have made a drawing on the whiteboard. I hope you can see it probably. Now the first thing that I didn't mention last time, but I will mention now, is that all the calculations I've been doing so far, and also will be doing forward from now, is actually in 1 dimension only. But when we're doing these lens calculations, we're doing it in planes. And that means that deflection angle is just not up or down, it is actually in a plane. So if this my fist is the lens, then the image would be out here somewhere, probably out here. And then we would have a y component of this distance and an x component of this distance. So it's a vector. This distance here is a vector. So let's just look at what we have in the lens equation. So we have on this drawing, we have the source plane, we have the lens plane, and we have the observer plane. Now I've just written the observer plane to let you know that of course we are also in 2 dimensions. So we are also, actually we're in 3 dimensions, but in this case we're in 2 dimensions. We are also in the plane. Then we have these distances here from the source plane to the source, and this distance here from, I'll just make a little dot here, from the lens plane, this distance here, from the lens plane to the image. And we have some angles. And also we have the distance from the observer to the lens, dl. We have the distance from the observer to the source, ds. And we have the distance from the lens to the source, dls. So let's take a look at the angles here at first. So from that we can derive, we can quickly see that the angle beta, which is a vector, as a function of theta, which is also a vector, is equal to alpha, which is a vector, of theta, which is also a vector, minus theta, which is a vector. Theta or theta is a little overdoing it, but this is the most fundamental equation in gravitational lensing. This is the lens equation. What you have to understand is that this lens equation is non-linear. That was the name I was talking about, the word I was looking for. So what does that mean? It means that if I have an image somewhere, this deflection here, alpha, here, if I know this, then I also know that there must be a source. That is given. If I have an image, then I also know that there must be one source. If I have multiple images that comes from the same thing, I know that also there is one source. If I have multiple images that isn't the same, then I know there must be multiple sources, but that's beside the point here. What is important to remember is that if you try to reverse this equation, it becomes non-linear. So we cannot say that if we have a source somewhere, we can't just predict how many images there will be. That is why when calculating, I will get into that further later on, but just for now, when calculating in the source plane, it is fairly easy because you don't have to invert anything. When calculating in the image plane, you have to invert this equation. It becomes non-linear, and that means you actually have to calculate for every possible scenario. You simply have to put as many different types of masses into the lens plane as you can, mass distributions, surface mass densities, and see which one of them gives not only the correct number of images, but also gives the best predictions on where the images will be. So now, in order to get this is just angles here, but in order to get an equation that we can more easily work with, calculate in order to find beta, we can look at some other equations, equations from this diagram here. And what we can find here by looking is that the angle alpha times the distance dl must be proportional or the same as this alpha hat angle here times the distance dls. So let's put that up. We say that alpha theta dl is equal to alpha hat theta dls. From now on, I will just assume that you understand that all these angles and distance, all these angles that I put up is vectors, because I don't want to write all those lines above it. They are vectors, and I will certainly let you know if some of them are not vectors any longer. By rearranging this a bit, we can get that alpha theta is equal to alpha hat of theta dls over dl. So if we put that into the lens equation, we get that beta is equal to alpha hat theta do it again. This is dls over dl, and this is also dLs over dl minus theta. I hope you can follow me on this, but it is simply just a question about taking this angle which you have here, up here, taking this angle and substituting it in there, and then you get this part here, alpha hat dLs over dl minus theta. Alright? So what we can also do is that we know I mentioned the deflection angle before. That is, when you write it in another way, alpha hat of this symbol, I can't remember what name is equal to 4gm over c squared, the symbol. Now we have that here, that symbol here, and we can find that this distance here is the same as theta times dl. Sorry, this is wrong. Sorry. This is horribly wrong. The alpha angle here, because we're looking at the image, it's not dl. It's that this angle here of the source, this angle here, alpha, source, image, is the same as that angle here from dLs. So that should be ds, this distance down here. Then we put ds in here, and the same here, ds. Now it fits. And then we have this distance here is the same as the angle theta, this theta, times the length dl. The length times the angle gives this distance here, this distance up here, right? Because we're using small angle approximation, that is why we don't need to take the tangent or the sine or anything like that. We can just multiply them together. If we put that into this equation here and rearrange it a bit, then we get, let's take them like this, then we get that alpha hat of theta to the vector is equal to 4gm c squared 1 over theta. Alright? Times dl, because we put that in there. If we put that deflection angle into this calculation here and rearrange it a bit, then we get that the deflection angle, beta, the position beta, I haven't really said what that is, so let's just take that right away. So the angle beta is the angle from the observer out to the source if we could see it in a straight line. This is this angle here. The angle theta, and let's just say that this line down here, I'll just make it a little bit more visible, is the line of sight going through, or the center line going through all the planes. Maybe that's a better way of saying it. And so the angle theta, this angle here, is the angle we see when we see the image. All right, and the angle alpha, this angle here, is that angle we have from the line to the source and up to the image. So that's the angle here, and beta is the angle here, and theta is the whole angle here, down to this line here. Alright? So the observables that we have, is actually theta. That's what we can see. We can see the positions of the image compared to the lens center, or the center of the lens, or whatever you want to use. Usually we use a defined center. Alright, so let's put that deflection angle in here. And I just have to be absolutely sure that what I'm telling you is correct. So I'll just find the deflection angle here in my notes. So substituting this deflection angle into the equation we have here, and then rearrange a bit, then we get that the beta as a function of theta is equal to 4gm c squared theta, which is a vector, times the distances dls, ds, dl. So now you can see that from this equation here, where we have only the true observable we actually have is this theta here, then we can substitute the deflection angle and some more calculations of distances into it. Actually, it's angles we calculate. And then we get an equation where we can find beta of theta by calculating the deflection angle 4gm over c squared theta. Again, theta is an observable that we have, times the distances dls, ds, dl, which, if we know the redshift of the source and know the redshift of the lens, then we can calculate all these distances here. So, in basics, going from an equation where you have two unknowns that we really can't calculate, because since we don't know the position of the source and the angle up to the source, we can't really find the angle alpha because we don't know where we should start, but we know where we should end. That's the position of the image. The only thing we can observe is the theta, this angle here. And we can also observe by taking the redshift. Usual way of finding redshift is using spectroscopy, but we can also find them on certain photometric redshift. If we know the redshift of the lens and we know the redshift of the source up here, which is actually the redshift of the image, but that's the same. Then we can find the distance dl and dls, and the distance dl and ds, and by using cosmological calculations we can also find the distance dls. Now in general we have that because the way we calculate cosmological distances, that is actually an integration, we have that ds is not equal to dl plus dls. That is very important to remember. So you can't just take these two distances here and then subtract them to get this distance here. This does not apply. Alright? I think that sort of sums up the introduction I wanted to give you to the lens equation. This is the most basic and fundamental equation. When you want to calculate, want to model these things, you go about it in a different way where you actually use matrices and tensors. Basically, a tensor can be described as a matrix. So that is one way to calculate it. It's more easier to do in a computer, but this is the basic idea of how you want to do it. Second of all, no, that's the thing. The last thing I just want to do is show you some images that I will also present later, but just to give you them, use them now, so you can have a look at them, of some of the objects that I have and will be working on in the future. And also to give you an idea of what it is that we can actually expect from gravitational lensing. So the first image you can see is this. It is from a cluster of galaxies called A1703 Limousin. It is by Limousin and others. It's from 2007, I think, maybe 8. It's published in Astronomy and Astrophysics, so you can find it if you want and take a look at it. Now you can see this object here, this galaxy is particularly special. So you just find something I can point with. It's particularly special because we have this interesting formation here, and then we have a counter image down here somewhere. This is an unusual formation, this is an unusual configuration, because usually we have arcs like this. See if I can find you. There's a very prominent arc here, I think. No, that's because it's a blown up image. Yeah, there's maybe it's hard for you to see, but there's a blue arc down here somewhere. I just try to deflect. You can see it there. There's an arc. Usually that is what we see, not this. So this is a bit special, and these are spectroscopically confirmed that they're from the same source as with the image down here, 1.5. Alright. Next object I'll be showing you is the object that I'm working on right now. It's this. It's called MACS, M-A-C-S, J0416. That's the position of it. And as you can see on this image, first of all, you have two large galaxies. That would immediately suggest that this is not compared to a bell, where we have one large galaxy and then smaller galaxies around it. Here we have two bright central galaxies, bright center galaxies. This. Alright, sorry for the interruption from the last part of the video. I'm afraid that this was full, so I had to unload it and reinitialize it, and then we can continue. But like I said, when you compare MACS J0416 with A1703, you see that this cluster has a bright center galaxy here and a bright center galaxy here, which suggests that this is a cluster undergoing collision. There's actually two clusters of galaxies that are colliding together. I think the local group and Sagittarius group in our local universe is doing the same thing, but it's actually two clusters of galaxies that are colliding together. And one interesting thing is that when you model these things, this is not my model, but it's one I've been redoing, or I am redoing, is that you can see. I'm sorry, there was another little interruption. I suppose they are coming in equal amounts this day, but as I mentioned before, this is not my model, but it is the model that is close to what I'm redoing. And as you can see here, hopefully, I'll try to make it as visible as I can without any dumb reflections. Let's see. Yeah, I think that's the best. But you can probably see that the bright galaxy, one of the bright center galaxies are here, and the center of the halo is out here. And as you can see here, the bright galaxy is here, and the center of the model halo is here. The model halo is the prediction of the model where the halo, that is the dark matter, the matter of all the cluster, is positioned. This is the center, and the same goes on here. And the last thing I want to show you, no, let's just take that. All right, so why is that interesting? That is interesting because we know from theory that dark matter particles should be collisionless. Gas, on the other hand, is not collisionless. That is why if you look at the composite image from, I think it's called the bullet cluster, you can see that part of the image is from X-ray observations, where you can see that the gas slows down, but the predictions of the model of the dark matter has just continued the collision. So the gas and the baryonic matter, some of the baryonic matter will slow down the collision, but the dark matter will continue. And that is why this prediction here is extremely interesting, because that would suggest that this model has, as it should do, included the gas, the mass of the gas, inside this halo calculation. It also suggests, compared to galaxies, that in a cluster, especially a non-relaxed cluster, that is a cluster in this case undergoing collision, the mass of the gas has a significant contribution. If the gas was insignificant, then the model would show that the center of these halos should be just above or close to this bright central galaxy. When you model A1703, you get, I think, that the center of the halo, the cluster halo, is somewhere around here, so close to the bright central galaxies. The last thing I want to show you is this. It's one of the recent plots that I made from my models. You can see the red line here. No, I just want to tell you what I did. So one of the things that you can do when you model gravitational lenses is you can use something called Biasion Statistics. In this case, it's called a Monte Carlo sampler, MCMC, multiple chains, I think it's called. Monte Carlo multiple chain, something like that. It's a Bayesian method that calculates the prior probability and after probability and all that jazz. From that model I've run, you get approximately 10,010 different models. From that I have extracted on this plot 100 models, 100 random models, run the calculations of the mass for each model, then plotted it. Now you can see an example of a single model plot right here, and then this plot here. That's just a lot of models plotted over, and this is what we did. The black lines are what we call 1 sigma confidence interval, or you can call it 6 to 8% confidence. That's your real own choice what you want to call it, but that's one of the things that you can do with this kind of models. Alright, the last thing I want to say is that the future for the models that I'll be doing is trying to create a potential for the gas in the cluster. Now we have found some suggestions that the gas actually contributes to the lensing in a significant manner. What would be very interesting is to try to incorporate the mass of the gas into the model as a separate potential profile, and then try to see where is the center and the size of the dark matter actually. Because if you have separated the luminous matter, what you can see, the gas, and these two into separate models, into separate profiles, and the last profile you have in that model should be the dark matter. Thank you for watching.